I'm from Oasis, and we're looking at sort of confidential contracts and confidential EVM, and what is like next generation contracts, which, so I think that the first thing we have to think about is well, what is confidential EVM? Why do we need this? And then I'll look into, so the current generation of smart contracts. What is the current generation? What are the technologies that they use? And the sort of kinds of things that you can do with them? And what can we do, what do we want from the next generation that solves a different set of problems? So I do want to start with a bit of context to try to give some idea of the problems. And overall, the big problem at the moment is because there's so much of the infrastructure that we rely on depends on trust. And it's not necessarily like a one-way process to reduce or remove the trust. It's like a war of attrition, and it takes effort and constant reevaluation because like trust is really simple, and trustless is often really, really difficult. So it requires forethought to be trustless, and like vigilance and analysis, and sometimes it is like a sort of 2 steps forward and 1 step back. As we can rely on trust as we become complacent and slip back into the path of least resistance. And as a whole, though, I do think it's heading in the right direction. And like secure enclaves, for example, are a big part of that move. We have them in our phones, in our payment cards, in our authenticated devices, and there's probably billions of devices right now that use them. There might be more secure enclaves than there are people on the planet, and if they're not, then there will be fairly soon. But right now, I'm focusing on the 2 steps back bit, right? So in an ideal world, everyone does the needful, everything works perfectly, although reality, it kind of sucks, right? So as a baseline for having trustless systems, we have disinterested parties. We can generally trust them through like reputation or economic or game theoretic incentives, or just plain old disinterest, right? So they've got nothing to gain or lose. But that's always not the best incentive, to keep a reliable system running smoothly if they don't care about it. So yeah, a lot of the time that doesn't really work. So we have regulations that try to enforce this, and it's very difficult to be a disinterested party if there's money or anything at stake. So we need to try and enforce this in meat space. And that's all because we're trying to design these resilient systems that really, in an ideal world, we don't need regulations to be enforced in meat space. We shouldn't necessarily need laws. They should just, in practice, they should work. And we want to enforce like this consistency and reliability through like real universal laws. So thinking of mathematics, cryptography, like code, silicon logic, and at the root of it, it all sort of boils down to either physics or like intractable logic problems. And we want to use these sort of intractable laws to create the systems, and we have to encode them in the rules of that system in a way which is self-regulating, it's self-enforcing, and it's like self-evident that it's correct. Unfortunately, there's an Australian politician who said, that the only laws that apply in Australia are the laws of Australia, and I beg to differ, because you didn't have to write a law to stop the people falling off the bottom of the planet. And they also tried to do some silly things, like in the US, they declared that cryptography is a munition, and they imposed export controls, and in some cases actively tried to sabotage it. And are they trying to do that to prevent people from creating systems which they can't control? I feel it's kind of sinister. If I can think of like an intractable logic problem or a mathematics problem, I should be able to demonstrate it, that it does work, that it is intractable, that it's resilient and autonomous. This is why I think we do really need cryptography and encryption. So signature schemes, multi-party computation, zero-knowledge proofs, and secure enclaves, and all of these things working together so we can protect us and protect our infrastructure, regardless of whatever the people in power in a year, 4 years, 10 years are going to change their mind on. And I try to describe it as we need to sort of wedge the door open so you can't ever close it. And this is the difficult route that we have to go down. So what are some strategies for security about how can we create this like trustable, resilient infrastructure? Part of that's like independence and autonomy at every layer, that when they're combined, they strengthen and reinforce the other layers. If we look at end-to-end encryption, like many times it's not really end-to-end. So a great example is like Ethereum RPC infrastructure. We have this resilient blockchain of variable execution of smart contracts, but you probably don't usually run your own Ethereum node or even like run a local fork of it. So you take the path of least resistance and you use an RPC provider. And your dApp needs to query the smart contracts and use SSL to securely connect to the RPC provider, and it does the query and returns the result, but there's something wrong with this, which is you're still blindly trusting the RPC provider with the unencrypted query. And it returns a result which is not verifiably correct. So again, you're doing all of this work, and then it's not end-to-end encrypted, it's not verifiable, it relies on trust. And you're not sure, like, are they keeping logs forever? Or if they say they don't keep logs, how do you really verify that? And the RPC provider may promise to be neutral. And they might promise to not censor your queries, or they might promise to evaluate your contracts faithfully against the data you request and not modify your results and not log your requests and access patterns. But just like with the politicians, they're only promises right now. And there's no sort of real enforcement of this that is independent of whatever the whims of the humans are involved. So it can change at any moment. And yeah, so because it's not verifiable infrastructure, you can't guarantee true neutrality, you don't really have privacy, and it's not enforced in any meaningful way. So you've basically just gone and circumvented everything that made it autonomous and independent, and you might as well, put all your stuff in a database in the cloud because it's going to be easier to use. It's a lot of these L3s is just overly complicated. Why do it the real way or just use the cloud? Stop sort of doing, I don't know, this stuff in the middle. They're kind of halfway solutions. They're making big compromises. And this isn't really where I thought Web 3 would be. And maybe it should be somewhere else. So the other problem is data. So we're trying to think up some analogies for like what is data? Like, is it like nuclear waste, or is it microplastics or asbestos? And unfortunately, it's everywhere, and we can't really recycle it. Like, what is data recycling? Most kind of data, we really don't want it to be recycled in any way at all, because the nature of it is that we can't put it back in the box once it's out there. But every cookie banner you see on the internet where you say yes or you just click the button, that's data recycling. And it took 10 or 15 years for SSL and HTTPS to become a standard, and a handful of more years for drive encryption to become the norm, because if it gets stolen on a train, you don't want them to access all your data. So now everyone's phones and your laptops, they're encrypted by default. And just as we started to encrypt all the servers and the devices, we move everything to the cloud, where it's all sitting basically unencrypted. So even though the servers may be encrypted, there's still hackers, sysadmins, the law, for example, can get access through the software that's running it. We've got the software updates where, sometimes we're not sure if it ever gets deleted. And now we're putting all of this unencrypted data on the blockchain. And like, due to how it's structured from the get-go, that's there forever, and we can't delete it. And when I think of blockchains now, I think of it's like the elephant's foot in the basement of the Chernobyl power plant, where for every benefit it gives us, it's also a little disaster that we're not sure is really happening until it's too late, and we've got all this data and it's out there forever. So I think one of the things to think about today is how can we combine all of these different technologies to have privacy and protection by default at every level, to have the sort of verifiable infrastructure, and ideally to prevent the unnecessary accumulation of data in public. So it's like waste data, right? And all of the blockchain history, it's a byproduct of an inefficient process. Ultimately, it would be nice to have to choose specifically what's made public, rather than having to try really, really hard to keep certain things private. So I'm going to try and get back on track, and a little part of all of this is stuff that we at Oasis work on. And I hope it fits into this stuff I've been talking about. And it's essentially confidential smart contracts. So we have an EVM-compatible chain, just because Solidity in EVM just happens to be what everybody likes, and it runs inside a secure enclave. And we're experimenting with this like small but important difference to find sort of new things which weren't possible without it. And I do like to look at like the early days of Ethereum, where we're trying to go, what can you do with smart contracts? And I think it's what can you do with confidential smart contracts? And there are some big problems that may or may not be solved with these in the next handful of years, but we want to see, we want to find out. So we need to make a big distinction, though. So transparent EVM, which is Ethereum, Polygon, Arbitrum, Optimism, or whatnot. And this also applies to all sort of transparent chains with smart contracts, not just EVM. So with a transparent EVM, the call data is not encrypted. Even if you encrypted the call data, it's like the parameters for the contract, a transparent contract can't keep that information private. So its runtime state is visible to everybody, and so is its storage. So the execution is verifiable and it's deterministic, but it can't, by design, really operate programmatically on encrypted data without delving into some really interesting areas of math or encryption, like snarks, multi-party computation. And you could have it like mediate encrypted communications, and you can have little bubbles of privacy, but it's limited to sort of subsets of the functionality. You don't have a full programmability. And as a whole, it's missing one critical thing, which is transparent EVM. It's not confidential or encrypted. And in the real world, that's really, really, really important. So I'm surprised it's as popular as it is. But it's popular because we have modularity and composability and like the verifiable nature and independence, and sometimes it's really fast. And in theory, there's no barrier to entry. So one of the beautiful things is you don't have to fill out a load of paperwork and compliance or set up a startup just to use it. You don't have to ask for permission. And generally, it's self-regulating and autonomous, and it's resilient, these are the properties that we really want out of the system. So realistically, it has its own laws, regardless of what the politicians that are saying this week or month or whatever, and that's in which jurisdiction. So we're really trying to create a system that means that we can't change our minds, and it's going to carry on independent of us. So I'll go very, very briefly over some of the details if you are familiar with Intel SGX. If you're an expert when it comes to this, I'm sort of fudging some of it for simplicity. But we have our smart contract that it runs in the secure enclave, and we have end-to-end encryption between the browser and the contract. So you have the contract that's inside the secure enclave, and we have a rotating call data key. So only nodes which are in the compute committee are allowed to have access to the current call data encryption key. And they have to prove that they're running a specific software stack with the most up-to-date version of our chain, updated BIOS, Intel microcode, for example. And only through that attestation process can they get access to the current keys. And that means that there is a cryptographically verifiable chain of signatures all the way down that says the software that I'm interacting with is part of this committee that has a key that I can encrypt stuff that only it can see, and I can verify end-to-end that it's only possible for this enclave to have that key. And with Oasis, we're using a compartmentalized key manager. So you can see it on the right there. And again, that also runs inside the secure enclave. So importantly, the confidential EVM nodes, they don't hold the master key. They're given access to a limited subset of the keys based on what they need to compute on a case-by-case basis. And so because execution happens in the secure enclave with encrypted memory, that means the node operators can't see the contract storage. They can't see the runtime state. They can't see the call data that you sent to the contract to invoke it. And if we look at like what is the sort of state of the art in comparison to that at the moment, and how does it differ from what we would like confidential EVM to be? And I think you have to make a distinction between like these single-purpose systems, so versus general verifiable confidential compute. And you can even go a little bit further and make a distinction between systems like ZK VMs or stuff that uses multi-party computation, fully homomorphic encryption, and something that has the right set of trade-offs. Like if we look at what is and what isn't feasible, what is realistic now, where are these trade-offs, So with the single-purpose privacy systems, they're really limited. You have like transactional privacy or encrypted communications and storage. That's like Monero, Railgun, or Signal and WhatsApp, or even your encrypted hard drives. Then you have things like Alio or Mina or even ZK EVM. But there's an important difference with everything that's ZK-based versus what I think confidential EVM should be. With all of the ZK-based systems, you can prove that you computed something, and the data involved in that computation, it can be confidential. In the example of like ZK EVM, confidentiality is not being taken advantage of. Nobody really cares that it's confidential because you have the succinct, short, verifiable computation proof that makes ZK EVM, something that's worth doing. But if you take if you want to make a DEX or an order book or something that uses data with interaction between lots of different people at the same time, that's really difficult to do with ZK-based systems because fundamentally, a contract to do this efficiently would need to have its own private state. You need to have something similar to the centralized exchange where they run the order book, they can see all the orders, but other people can't see each other's orders. So you can't really do that with a ZK EVM, at least not easily. So if you have a confidential contract that can run the order matching algorithm using all of this data, then that just, it makes sense. It does something that you can't do easily with the other tech. And you can do it with a combination of like multi-party computation, fully homomorphic encryption, but that's really, really slow and incredibly tedious. And if you've tried it, try to convert some of these algorithms into circuits that you can prove with multi-party systems. You can pass to millions and millions of gates, and it starts taking hours and hours to get the proofs, which slows everything down. And really, if we're looking at the trade-off of using a secure enclave with little to no overhead in comparison to the other sort of state of the art, I think that's hitting the sweet spot for me, and that's why I work for Oasis rather than on ZK or MPC stuff, because I would be if these guys didn't exist. So something that's really, really important for like smart contract chains is like composability. So that's the contracts that are interacting with each other. Because you've got like programmability, and functions can be added later on by anybody. So they can make it do stuff that it wasn't originally intended to do. The contracts can be upgraded. You can have even like modular plugin-based architectures. And with like a confidential EVM that's using trusted execution, you don't have to design all of this up front. And really the value comes from the composability. And if you have a lot of unintuitive constraints that are pushed on you, you have to design systems in a very different way. So yeah, we want something that's compatible with EVM. We want something that has the minimum number of modifications that's necessary for your app. So maybe a little wrapper plugin that adds encryption, but to your dApp that you otherwise don't have to rewrite everything. Although, we also want to be able to emit public information. So if we're defining a confidential EVM, the events should be public. It should be able to decide what is and what isn't private on a case-by-case basis. So the problem is that there are a few other complications that come with designing a confidential EVM-style system. And one of the constraints we had is to prevent denial of service, you can't really anonymize the gas payer. So you see which account's paying gas and the gas price and the destination address and how much gas was used in the transaction. And of course, like the events in which contracts emitted, the events is also public. And there are some subtle differences that can make smart contract development difficult. So one of those that surprises people is you can't impersonate accounts. So if you had a password manager, you wouldn't want anybody, like on Ethereum, you can simulate a transaction from anybody to any contract and see how it would how it would operate if you did that. But if you have a password manager, you don't want somebody to be able to execute the password manager as you and say, dump all my passwords. So we have to come up with a different way of authenticating users. And one of those is like, think of the sign-in with Ethereum. If we need a confidential EVM, we need a different way of authenticating people, and that's very different from just connecting your wallet. So there are a couple of places where everything's designed for transparent EVM, and we're only just discovering these problems that have sort of significant UX impact. So one of the things we're doing is we're just setting the message sender to 0 if it's a query that's not signed. And that's kind of like a protective measure to prevent people from relying on information that could be impersonated or is not trusted. I've got 2 minutes. So the second one is side channels. So you've got the gas usage. That can reveal which code path has been taken. And this does make it a bit brittle. And also the order of events that are emitted is also a point where, in comparison to transparent EVM, you have all of these problems that you didn't have to think of before. And, that's a problem that people don't usually think about. So the other thing is confidential EVM allows you to solve some problems in radically different ways. So you can have a contract that generates a key pair, and rather than having a relayer infrastructure, you can have the contract sign a transaction for you and pay its own gas from an account that manages it. And if you look at all of the Ethereum standards as they are now and you reimagine them from the confidential EVM perspective, you can get rid of a lot of the external infrastructure. You can take completely different approaches to problems. And also confidential standards. None of our standards really have confidentiality at the root of it. So there is opportunity to reimagine what would the Ethereum ecosystem be like if these contracts were encrypted and confidential. And one of the things that comes with that is there are some really, really useful building blocks that you just have to have accessible. So one of those is a random number generator that the contract can generate key pair, secret keys from. And then, well, if you're generating secret keys and key pairs, then why not have signing algorithms for all of the widely supported curves like the Bitcoin curve, ED25519, and also the NIST curves. There is the rest of the world out there that's not using all this Bitcoin-specific technology, right? And then encryption, decryption, to be able to have a contract that passes encrypted data through users back to itself or back to other contracts. This is also a really useful primitive that, without, if you have to implement in Solidity, it just takes a lot of time, so we have to provide this as standard. And one of the big problems we're looking at is how do we interact with Web 2 systems? So if Web 2 systems are all using NIST standards, and you can have a contract that can act pretty much autonomously, we need to be able to support, for example, the cryptography that's used to verify Amazon Nitro enclave attestations. And with that kind of interaction with verifying attestations from other cloud providers or from hardware providers, you can establish a root of trust in a confidential chain where it can then start controlling and orchestrating stuff in a way that you couldn't necessarily do before. And I'm running out of time. So I think that the next question really is, can we do confidential AI? We do have a bounty for this. And there is a big question of, with end-to-end encrypted AI, are we making sacrifices now just because we need to get to market to get GPT, and we're releasing all of this data into the public, and it's being collected, and it's going to be reused and whatnot. So we do have bounties and our hackathon, of course, which we're sponsoring. And there is an extra $2,000 bounty if anybody wants to try and answer that question of how does confidential AI and blockchain work together. And of course, we've got example apps. So please, I'll be upstairs. If you're hacking, come and talk. And thank you. That's me done for today. Thanks a lot.